Earth. A unique planet, restless and dynamic. Continents shift and clash. Volcanoes erupt. Glaciers grow and recede. Titanic forces that are constantly at work, leaving a trail of geological mysteries behind. In this episode, we investigate the formation of the Rockies, a North American mountain range shrouded in mystery, flanked by huge slabs of rocks with ancient sea fossils buried high in its slopes, and crowned by jagged peaks that geologists believe were once double the height they are today. Scientists piecing together their story uncover evidence of massive ice sheets, collapsing mountains, and explosive volcanic eruptions. A geological history that brings us one step closer to understanding how the Earth was made. The Rockies, a majestic mountain range towering high above the American West. It's the longest chain in North America and the third longest in the world, stretching over 3,000 miles from New Mexico through Colorado, Wyoming, and Montana, and north into Canada. For decades, geologists have been puzzled about how this giant mountain range rose from the plains. The investigation begins with a specific type of rock.
Here we are in the heart of the Rocky Mountains. We're in an amazing place to begin with. And right here at Red Rocks, we're in the midst of an amphitheater of rock.
"13 miles west of Denver, Colorado, two 300-foot-high sandstone monoliths slope 45 degrees into the sky. Each is taller than Niagara Falls. Together, they form the walls of a unique musical venue. But there is more to these rocks than fine acoustics. These rocks tell the story of how the Rocky Mountains were made. The story begins with a mystery. 8,000 feet high in the Colorado Rockies, 60 miles northwest of Boulder. All kinds of strange impressions are found in rocks scattered over the landscape.
We find more than 100 species of marine animals right here at this site. We find sharks, we find lobsters, crabs, we find beautiful fossil clams, which are all over the place.
These fossils are crucial evidence of what existed here before the Rockies emerged.
We're sitting at about 8,000 feet in the middle of the Rocky Mountains. And so when these fossils were formed, this was below the level of the ocean. This was below sea level.
This area was covered by a vast inland sea. It existed for over 30 million years and stretched from Utah to Missouri and from the Gulf of Mexico to the Arctic Sea.
And at this very site, it would have been very warm, almost tropical. And so envision maybe a day on the beach in Florida or something like that.
This warm climate attracted a unique type of creature that left behind large, round imprints in the rocks. These fossils would play an important part in the investigation.
This fossil here is a giant fossil ammonite. And this animal, this coiled shell right here, is a relative of modern-day squids. So the closest living relatives today are squids, nautiloids, octopuses, things like that. And so in this big coiled shell here, the animal would have lived at this end, and its tentacles would have stretched out right here. And this animal is really quite remarkable. It's about the size of a truck tire. And this is incredible because most ammonites aren't this big.
Nowhere else have scientists found a greater number of these prehistoric creatures than here. Miller has come up with a theory why so many of them came to this area.
We think this particular fossil here was a female ammonite. And we think that in part because male squids are smaller than female squids by a lot. So just looking around the fossil deposits here, we found a male ammonite, this small one here. So compare the size of this guy to this very big one here. And when we look across this landscape, we we find mostly these big ammonites. And so we think that maybe all these females got together to spawn and then died after they spawned.
When the ammonites became extinct, the map of North America looked completely different. To the north, the Canadian Rocky Mountains already existed. To the south, the American Rockies had yet to rise. The date of the ammonites' extinction holds a key to when they first emerged.
These animals died about 70 million years ago in the middle of the Western Interior Seaway. And so we know at that time, about 70 million years ago, that this site was below sea level. So we know then that the Rocky Mountains had to rise from that seaway sometime after 70 million years ago.
Today, all that is left from the ancient sea floor are these fossilized remains high in the Colorado Rockies. Next, geologists needed to find out what pushed the seafloor up. The investigation moves to these slabs of rock flanking the Rockies just outside Denver, Colorado. They are known as the Flatirons, and they are part of the same formation that make up the Red Rocks Amphitheater. These slabs of rock are unusual because they contain holes. Holes that make the Flatirons appealing to climbers and geologists alike.
So when we go climbing in the Flatirons, we're climbing on really nice handholds. In some cases, handholds that have been formed either by the pebbles in the rock or by zones of fine-grained material that are easily removed by erosion, the shales and the siltstones. Those layers get removed, leaving a notch for the hands to go in, and it makes for fantastic climbing.
The holes are a clue as to how these strangely tilted flatirons were formed.
The layers themselves, the different grain sizes in the layers, the silt, the sand, the pebbles, this tells us that these are sedimentary rocks.
Sediments form in water when sand and small pieces of rock settle on the ground. Over millions of years, they get compressed into layers of rock. Taking a closer look, Lester can find out more about the surroundings they formed in.
These were not just deposited in any kind of sedimentary situation, but they were deposited in rivers capable of transporting big particles and busting them up as it goes along.
Sheets of sand and gravel built up a thick sedimentary bed like a layered cake. But stream deposits are rarely more than a few degrees from horizontal.
These rocks, you can see the layers, and the layers in the Flatirons behind me are 60 degrees.
Something caused these vast slabs to be tilted. The investigation moves 10 miles northeast to Flagstaff Mountain, located in the outer ranges of the Colorado Rockies.
I'm standing here right next to a miniature Flatiron. It's tilted like the Flatirons at about 60 degrees. It's steep. How'd it get that way if it was originally a stream gravel deposit?
The answer lies in the darker rock underneath. It is granite and looks completely different to the Flatiron rock above.
There's no layering in this rock, unlike the Flatiron rock, which does have layering. There's no pebbles in this rock, unlike the Flatiron rock, which does have pebbles.
A close-up investigation of the granite reveals that it is full of minerals. This offers another clue to how the Rockies emerged.
So I've picked up this granite here, and taking a look at it, I see quartz and feldspar and a little bit of mica in here, very characteristic of a rock like this that has cooled from a magma, from a liquid rock.
Among the minerals is iron. It is responsible for the dark color of the rock. The precise quantity of iron tells scientists the depth at which the rock was formed.
So we've taken this rock into the laboratory, and we do the chemistry on this rock, and we can actually determine that not only did it cool and crystallize at depth, that depth we can estimate at about 15 miles down. It's now at the surface. How did it get here? It's been pushed up by the rise of the Rocky Mountains, and in doing so, look what it's done to the Flatiron.
Scientists investigating the Rocky Mountains have found two clues about their early history. Ammonites on a site 8,000 feet high are evidence that the area was once under the sea. Traces of iron in granite is evidence that rock pushed up from 15 miles below the surface, tilting the Flatirons. And it didn't just happen here, but along approximately 1,000 miles of the American Rockies. Geologists now needed to find out what monumental forces were responsible for this massive upheaval. "100 million years ago, most of North America was covered by a vast inland sea. 70 million years ago, the sea retreated, and the Rocky Mountains began to rise, forming a great mountain range. Scientists trying to piece together their geological past needed to solve the mystery of what lifted them up. A force capable of that amount of heavy lifting would have to have been on a global scale. Geologists believe this force was caused by plate tectonics. The Earth's crust is broken up into a series of interlocking plates. These plates are continuously on the move. Over millions of years, they collide and break apart, forming new continents and geological features around the world. When the Rockies formed, two of these plates smashed into each other at the American West Coast.
What we know is that at the time of this granite uplift, on the western margin of North America, ocean crust, an oceanic plate, was subducting beneath the North American plate, and it was doing so at a high rate of speed. As such, it was transferring stress into the interior of the continent.
As the two plates moved towards each other, they squeezed the crust. Over millions of years, it folded and buckled, forming tall mountains. This was the birth of the American Rockies. But a mystery remained. How did the collision of two tectonic plates at the western edge of North America cause the rise of the Rockies 500 to 1,000 miles inland?
Mountain ranges that form on the margins of continents are pretty easy to explain. Or where continents have collided. Where India slams into Asia, we get the Himalayas. Where oceanic crust dives beneath the continental margin in the northwest, the Cascades. Or in South America, the Andes Mountains. But these mountains here, in the middle of a continent, are much harder to explain, and they've been an enigma for decades.
Only recently, geologists have come up with a plausible theory. They suspect the Rockies formed along a line where the crust is very fragile.
What happens when the continent gets compressed, especially if there's a weak zone or a zone that's prone to buckling? It rises. That's what's brought this granite to the surface.
Geologists now understood how the Rockies rose, and they had a date for when it happened. But what were these early mountains like? How do they compare to the mountains of today? On a site in the Rockies 70 miles northwest of Denver, geologists find a clue.
Mountains that we see here today aren't the mountains that were around millions of years ago. They're always evolving. Rivers are shifting, peaks are shifting. It's a very dynamic process. It's almost as if the mountains are alive themselves.
Miller sets out to estimate the height of the early mountains. But how can you measure something that is no longer there? Once more, fossils provide the evidence he is looking for.
What's amazing about collecting fossils is that you're really the first person to see this when you crack open a rock. It's the first time it sees light again after 60 million years.
Miller has uncovered a 60 million year old fossilized leaf. It's from a tree that grew here just 10 million years after the Rockies began to form. And intriguingly, this leaf holds a clue to the height of these early mountains. Or more precisely, it's the edges of the leaf, known as leaf margins. Botanists know that in colder temperatures, the margins tend to have more teeth than leaves that grow in warmer areas.
Leaves with teeth do better in colder climates because teeth are actually really advantageous in jump-starting growth at the beginning of the growing seasons. In this case, you can see this beautiful fossil leaf here with teeth, and each of the teeth are little hotbeds of photosynthesis. So when that leaf first comes out of the bud, it gets a jump start on leaves that don't have teeth.
Miller uses this information to find out about the height of the young Rocky Mountains. In a simple but powerful technique, he compares the number of leaves with teeth to those without.
If you go to a particular area and you pick up all the species of leaves that are there from the trees that are growing in that area, and you compare the number of species that have teeth to the number of species that have smooth margins, that gives us some idea of what the temperature is.
So the higher the proportion of plants with jagged edges compared to plants with smooth edges, the colder the temperature of the site. And the colder the temperature, the higher the mountain.
So if you got into a hot air balloon here today and you floated straight up into the atmosphere, the temperature would decrease in a very predictable way. And it turns out that for about every mile you go up in the atmosphere, you lose about 20 degrees Fahrenheit. And so if we know how temperature changes with elevation, we can back out elevation from those estimates of temperature.
To work out the height of the early mountain, Miller needs to compare samples from two areas, one at the base of the mountain and one at the top. Fossils found at the base of the Rockies near to present-day Denver have an amazing story to tell. These ancient leaves are incredibly similar to plants growing in the tropics today.
So after the Rockies rose, down in the area of Denver, it was subtropical and tropical forests. We had palms and cycads and canopies like we see in the tropics today. Up here, we had a forest that looked probably more like a forest that grows in North or South Carolina on the east coast of the U.S.
By comparing the ancient fossil leaves from the top of the mountain with fossil leaves from the foot of the mountain, Miller has come up with a surprising conclusion.
Turns out that the fossil leaves here are predominantly toothed as compared to those that are in Denver, which are predominantly smooth margin. And it turns out the ones in Denver grew in a climate that was about, on average, about 75 degrees Fahrenheit. The ones up here grew in a climate that was probably about 50 degrees Fahrenheit. So if we know how temperature changes with elevation, that means that this site, when these fossil leaves were deposited, was about a mile higher than Denver. Today, it's only a half a mile higher. So 60 million years ago, the mountains would be twice as high as they are today.
After the Rockies emerged from the sea, it took them 10 million years to rise. 60 million years ago, they reached spectacular heights of 28,000 feet, rivaling the Himalayas today. The deep history of the Rocky Mountains is beginning to take shape. A weak line in the crust explains why the Rockies rose 500 to 1,000 miles inland. Fossil leaves show that the young Rocky Mountains were once nearly twice their size. Half of the rock that formed them originally has vanished. Scientists are now trying to unravel the processes that cut them down to the size they are today. Of the Rockies are trying to discover what happened to the billions of tons of rock that went missing. The investigation starts with a mystery at the Owl Creek Mountains in the Wyoming Rockies. The mountains are sliced by a river that has formed a deep canyon.
Well, the Wind River is very perplexing. It chose to take a straight path right through the core of a major mountain range. This is not the way that rivers normally act. Usually they'll take the easiest route, which is downhill. But this river cut right through a major mountain range and has been a mystery. It is a very perplexing issue to early geologists in the region.
This river led to confusion as early as 1806, when Meriwether Lewis and William Clark mapped the area during their famous expedition to explore uncharted territory in the West. When they came to the area around the Owl Creek Mountains, they assumed there were two rivers. North of the mountain flowed a river which they named Bighorn, thinking it was different to Wind River in the south. But later surveys showed that the Bighorn and Wind River are in fact one river that channeled through the mountain. Recently, geologists have come up with a possible answer. An answer that could also explain what happened to the once towering peaks of the Rockies. They proposed that millions of tons of rock eroded away, filled in the valleys, and covered the lower parts of the mountains. It completely changed the terrain.
At one point in ancient history, the basins in Wyoming were filled with sediments that had eroded off the mountains. This allowed the river to be at a higher plane and meander wherever it wanted to on its course.
As the water flowed, it carved deep into the sediments and rock underneath.
Eventually, it cut down a channel into the mountain and eventually excavated right through the mountain.
But this is just a theory. Now geologists needed to find proof on the ground. The search is on for the rock that eroded from the early Rockies. The investigation moves to a series of 1,000-foot-tall hills in the Powder River Basin in Wyoming. Known as the Pumpkin Buttes, they stand tall in an otherwise wide, empty landscape. Hidden behind the horizon are the Bighorn Mountains, the nearest range of the Rockies. These hills are not formed from solid rock, but a collection of rubble.
This rock, which we find all over the top of Pumpkin Buttes in Wyoming, is a granite. The closest granite we find to this area is the Bighorn Mountains, nearly 100 miles to the west.
The round shape of the granite rocks is further proof that they traveled from afar. Tumbling downhill in rivers and landslides rounded them on their journey over millions of years. This was a crucial step in the investigation tracing the missing rock from the early Rockies. Rock and cobbles eroded down from the Bighorn Mountains and filled up the basin to at least 1,000 feet, the height of the Pumpkin Buttes.
Pumpkin Buttes are unique because this used to be the actual surface level of the basin itself. The rest has been eroded away, 1,000 feet of sediment to the basin that we see now.
But the rubble found here is nowhere near enough to have covered the Owl Creek Mountains. McLaughlin traveled to Darton's Peak, 100 miles west in the Bighorn Mountains. On a cliff 9,000 feet high, he finds granitic cobbles that are strikingly similar to the ones on the Pumpkin Buttes. They, too, are from the core of the Rocky Mountains. But the story of the eroding Rockies wasn't over yet. After erosion turned the landscape into a gray cobble field, another disruption happened. Evidence for this is a layer covering the top of the cobbles.
It's very light, it's very fine-grained. It's actually a volcanic ash. As you can see, it's made of very, very fine-grained sediments compared to this boulder conglomerate, which is made up of big hunks of rock. It sits directly on top of this unit, and it was laid horizontally from mostly ashfall.
This fine-grained ash suggests huge volcanic eruptions nearby. They spewed out thick clouds of hot air, ash, and volcanic rock, which settled on the ground. Radiocarbon dating the rock revealed that it happened 25 million years ago.
Ash was deposited as it came out of the sky as plumes. Most of it came from the west and was deposited in basins across Wyoming.
After the lower Rockies were buried by their own rock, volcanic ash settled on top and covered the area with a thick white sheet.
At the time of the deepest basin fill of this volcanic material, all you would see in this area would be the very tops of the peaks exposed. The rest would be large, extensive lateral ash sheets.
Erosion and volcanism completely transformed the terrain and buried the Rockies. But then, over millions of years, rivers flushed out the eroded rock. Most of it is thought to have ended up in the Missouri and Mississippi rivers, from where it was transported into the sea. What's left are the mountains we see today. This also confirmed the theory geologists had about the formation of Wind River Canyon. The incredible amount of infill buried the Owl Creek Mountains. Wind River flowed on top and began carving into the mountains, creating the canyon we see today. The investigation into what happened to the early Rocky Mountains reveals two major clues. Granite found on the Pumpkin Buttes is evidence that the early Rockies dumped their eroded rock into the basins. Wind River Canyon, cutting straight through the Owl Creek Mountains, is evidence that the Rockies were buried by their own debris. The once mighty Rockies had now been cut down to nearly half their original size. But the story was far from over. Before they became the mountains we know today, they would have to endure an even greater assault. "70 million years ago, a great inland sea disappeared and the Rocky Mountains emerged from the seafloor. 60 million years ago, they reached their peak height, twice what it is today. Then, for millions of years, the Rockies slowly eroded away to half their original height, until 3 million years ago, another dramatic chapter in their story began that would transform them into the mountains we know today. Geologist and photographer Bob Anderson takes to the air. He is looking for clues that will tell him how the mountains have evolved. First, he flies over Boulder Canyon in the Colorado Rockies. It is an area that has remained almost unchanged over millions of years.
So this is Boulder Canyon we're flying up right now, and you can see how the river has incised maybe a few hundred feet down into otherwise relatively rolling terrain.
The mountain peaks that existed on the young Rocky Mountains were rounded off as rivers and streams eroded the rock.
It's this rolling terrain that the landscape looked like in the aftermath of the mountain building event that ended about 50 million years ago.
But as Anderson climbs higher to Long's Peak in the Rocky Mountain National Park, the terrain changes. Instead of rolling hills, there are rugged mountains with steep, jagged cliffs. It's evidence that another force has been at work. The most famous of these cliffs is the Diamond. Named for its shape, it's a vertical wall with a sheer 900-foot drop. The summit, about 45,000 square feet, is the same size as a football field.
Well, we're flying beside Long's Peak, one of the biggest climbing challenges in the Rockies. For a century, it's been a climbing mecca. It's a gorgeous, intact piece of rock.
This awesome wall is the most difficult climb in the whole of the Rockies. Since it was officially open to climbers in 1960, has claimed over 50 lives. Back on the ground, Anderson is looking for evidence that will reveal the processes that shaped the jagged peaks. On a hillside, he finds mysterious large boulders scattered across the valley floor. A closer look uncovers some secrets about their origin.
Well, I'm standing in front of a rounded boulder that itself is sitting on a smooth bedrock outcrop. Both the boulder and the outcrop are covered in lichen here of green to black to gray colors, and therefore I had to whack off a piece of the rock in order to see inside the rock. And indeed, it is different. The minerals that I see and the texture of the rock is different from the underlying rock, and therefore the rock is a foreign to this particular site.
Anderson searches the ground for more clues as to how this massive boulder got here. Nearby, he finds a smooth surface with very fine scratch marks.
I'm sitting on a polished surface. This little piece right here is smooth to the touch. And if I look at it in a certain way that the light glints off of it just right, I can see that there are scratches running in this direction across the surface.
The only force that could have produced these fine parallel scratches on the rock is ice. And lots of it. It's a clue that a massive glacier once filled this valley.
And that tells me that the glacier came down valley, came across this surface, and eroded it. Each one of these scratches corresponds to a sand grain embedded in the soul of the ice that, just like sandpaper, smooths off the surface. So zillions of sand grains over thousands of years will have eroded this surface smooth.
As glaciers flowed down the valley, they picked up rocks and grit. The ice pushed down on these cutting tools with the weight of over 1,000 fully loaded garbage trucks. It left scratch marks all over the Rockies up to 1,000 feet high. This is evidence that a massive wall of ice covered this part of the Rockies and shaped the mountains. The ice ripped out the rock from the valley walls and left behind the jagged cliffs and rugged edges.
For the last few million years, perhaps 3 million years, glaciers have come and gone from the Rocky Mountains. And every time they come across the landscape, they're capable of eroding that landscape at rates that are perhaps fractions of an inch per year. Meaning that over the course of one glacial cycle, you perhaps erode 10, 20 feet of rock.
Ice also created the broad canyons. With every ice age, new glaciers ground their way down V-shaped river valleys and turned them into broad U-shaped canyons.
For the glacier, the whole valley is its channel. So any place where the glacier touches the wall, it's capable of eroding it. And therefore, the walls will be made more vertical on the edges and be flattened on the base until it gets to now a U-shape, which then propagates downward.
Ice also explains the presence of these boulders. They hitchhiked at the bottom of a glacier down the frozen valley. When the last ice age came to an end and the glaciers melted about 10,000 years ago, the boulders were left behind. Scientists had found two pieces of evidence that were responsible for the jagged looks of the Rockies today. A solitary boulder far into the area could have only been transported here by ice. Striations showed scientists that a glacier at least 1,000 feet thick covered the Rockies. Ice was responsible for the dramatic shape of the Rockies today. But the mountains keep evolving. Recently, scientists discovered alarming evidence that they may collapse into a deep rift. For the last 70 million years, compression, erosion, and ice have sculpted the Rocky Mountains to their present formation. But the geology that created this impressive mountain range has also the potential to destroy it. Over the last 25 million years, a gigantic rift has been opening up at the southern end of the Rocky Mountains. It stretches over 160,000 square miles, and travertine rock is made out of calcite, the same material that builds up limescale. These rocks grow very rapidly, some enlarge by a few inches per month.
About a liter of the water will be able to drop out or precipitate a little pile of calcite about as big as an aspirin tablet.
Like limescale building up in a hot water kettle, travertines form around warm springs. Measurements confirm that water temperature around the travertines is roughly 77 degrees. Besides the ability to build rock, this hot water has more secrets to tell. Laura Crossie and Carl Karlstrom have a hunch that the water is warmed up by heat from the Earth's interior, rising up through cracks in the rock. They form as the Rift Valley pulls apart. Climbing down a cave 25 feet below the surface, they are hoping to find further evidence. The water contains microbes. They are microscopically small organisms. Most of them consist of only one cell. When scientists analyzed their genes in the lab, they found something remarkable.
What we found in springs like this by doing the DNA analysis is that the microbes that are coming up these faults are much more like what we find at mid-ocean ridges than like the rivers and streams we would expect in a continental setting.
Mid-ocean ridges are very long mountain chains under the sea. Just like the Rift Valley, they also form in geologically active areas where lava constantly erupts and builds up new crust. Any living organism surviving down there has to be able to cope with these hot conditions.
The springs here and the mid-ocean ridge settings are also characterized by the upwelling of deep hot fluids from within the Earth, indicating that these both are connected to that deep tectonic setting.
The microbes suggest deep tectonic forces are at work, but there is even more compelling evidence. Karlstrom and Crossie find an unusually high amount of gas bubbling up through the water.
These samples are kind of fun because it looks like an empty glass vial, but it started out full of water, and then we turned it upside down in the water, and the gas displaced the water until it's full of gas.
A lab analysis identifies the gas as helium. This is the conclusive evidence that deep tectonic forces are at work here.
The helium is the most interesting gas for us. It's the smoking gun of evidence for where these fluids have come from. There's two forms of helium, but it's the helium-3 that we're most interested in, and that form of helium is only derived from the Earth's mantle.
The mantle is a part of the Earth's interior, 30 miles below the surface. It is made up of hot, molten rock. In areas where magma moves up, pressure on top of it decreases and gases such as helium are released. They find their way through faults and cracks until they reach the surface. So helium gas is conclusive proof that geological forces deep under the Earth are building up. And the effect it will have on the Rockies is devastating.
The Rio Grande Rift is an area that's tectonically active in a different way than you think of building of mountains. This area is the next stage in the life sometimes of a mountain belt, where it starts to collapse, it starts to extend.
As hot magma surges upwards from 30 miles below the surface, it forces the area on top to spread. The surface stretches and thins and opens up a deep chasm. As the rift opens, the mountains to each side crumble into the valley.
You can think of a piece of taffy that's being stretched, and it might break on the top, and those breaks would lower pieces of they would drop down, and then once you have what's called a fault valley, then the sediments wash in from the high mountains. It's an immense structure. It's about 6 miles deep. It's about as deep as Mount Everest is high. But it's when you drive across it or you look at it from any vantage point, you don't see that entire depth because it's all been filled with sand and gravel progressively as the extension took place.
Today, the Rio Grande Rift stretches over 160,000 square miles from Mexico in the south, where it's broadest, to Colorado in the north, where it's only just begun to open up.
This rift is propagating northwards into the higher Colorado Rockies. What's going to happen to Colorado? Those mountains will probably collapse by rifting as the rift propagates, zippers northward. And you can visualize that what's now in Colorado is more similar to what was in New Mexico before the Rio Grande Rift opened and before the mountains collapsed.
Looking ahead in the distant future, there could be challenging times. The tectonic forces that created the Rockies could eventually lead to their destruction.
When we think about the great continental rifts, East African and Rio Grande Rift, the question arises, is the continent going to split apart here? If this rifting carries on, are we going to have beachfront property right here in New Mexico? And the realtors are very interested in this, but so are the geologists.
The formation of the Rocky Mountains is a remarkable story. 70 million years ago, the death of ancient Ammonites marked the rise of the Rocky Mountains from the retreating inland sea. 60 million years ago, leaves with jagged margins grew on the mountains that were twice as high as today. 10,000 years ago, a solitary boulder marked the retreat of the last glacier that sculpted the Rockies. And helium gas in the Rio Grande Valley today is a clue that the area deep under the surface is active again. If rifting continues and the Rio Grande Valley widens, the area of the Rocky Mountains could one day rip apart. A new sea would move in, like the vast inland sea that covered the area 70 million years ago. The Rocky Mountains, the great backbone of North America, would slowly disappear, and the continent would once more split.
They are squids, nautiloids, octopuses, things like that. And so in this big coiled shell here, the animal would have lived at this end, and its tentacles would have stretched out right here. And this animal is really quite remarkable. It's about the size of a truck tire. And this is incredible because most ammonites aren't this big.
Nowhere else have scientists found a greater number of these prehistoric creatures than here. Miller has come up with a theory why so many of them came to this area.
We think this particular fossil here was a female ammonite. And we think that in part because male squids are smaller than female squids by a lot. So just looking around the fossil deposits here, we found a male ammonite, this small one here. So compare the size of this guy to this very big one here. And when we look across this landscape, we find mostly these big ammonites. And so we think that maybe all these females got together to spawn and then died after they spawned.
When the ammonites became evidence of massive ice sheets, collapsing mountains, and explosive volcanic eruptions. A geological history that brings us one step closer to understanding how the Earth was made. The Rockies, a majestic mountain range towering high above the American West. It's the longest chain in North America and the third longest in the world, stretching over 3,000 miles from New Mexico through Colorado, Wyoming, and Montana, and north into Canada. For decades, geologists have been puzzled about how this giant mountain range rose from the plains. The investigation begins with a specific type of rock.
Here we are in the heart of the Rocky Mountains. We're in an amazing place to begin with. And right here at Red Rocks, we're in the midst of an amphitheater.
These fossils are crucial evidence of what existed here before the Rockies emerged.
We're sitting at about 8,000 feet in the middle of the Rocky Mountains. And so when these fossils were formed, this was below the level of the ocean. This was below sea level.
This area was covered by a vast inland sea. It existed for over 30 million years and stretched from Utah to Missouri and from the Gulf of Mexico to the Arctic Sea.
And at this very site, it would have been very warm, almost tropical. And so envision maybe a day on the beach in Florida or something like that.
This warm climate attracted a unique type of creature that left behind large, round imprints in the rocks. These fossils would play an important part in the investigation.
This fossil here is a giant fossil ammonite. And this animal, this coiled shell right here, is a relative of modern day squids. So the closest living relatives today
restless and dynamic. Continents shift and clash. Volcanoes erupt. Glaciers grow and recede. Titanic forces that are constantly at work, leaving a trail of geological mysteries behind. In this episode, we investigate the formation of the Rockies, a North American mountain range shrouded in mystery, flanked by huge slabs of rocks with ancient sea fossils buried high in its slopes, and crowned by jagged peaks that geologists believe were once double the height they are today. Scientists piecing together their story uncover
Theater of rock.
"13 miles west of Denver, Colorado, two 300-foot-high sandstone monoliths slope 45 degrees into the sky. Each is taller than Niagara Falls. Together, they form the walls of a unique musical venue. But there is more to these rocks than fine acoustics. These rocks tell the story of how the Rocky Mountains were made. The story begins with a mystery. 8,000 feet high in the Colorado Rockies, 60 miles northwest of Boulder. All kinds of strange impressions are found in rocks scattered over the landscape.
We find more than 100 species of marine animals right here at this site. We find sharks, we find lobsters, crabs, we find beautiful fossil clams, which are all over the place.